Hello viewers, in today's session we are going to discuss another important and very conceptual problem from definite integrals. And in this session we are going to discuss this problem where we are given a function f which is defined from this set, that is the closed set from 0 comma 1 to the set of real numbers, and we are given this integral, that is 0 to sine x f of t dt is equal to square root of 3 divided by 2 pi x square, and we have to find the value of f of half, right? So here in this session we are going to make use of the famous Leibniz integral rule to solve this problem, right? So let us first see the statement of Leibniz integral rule, and then we'll see how we can easily solve this problem using the concept of Leibniz integral rule, right? And moreover here this domain, that is the function f has this domain, that is the closed set 0 comma 1, and this domain is going to play a crucial role, right? So let us start. Now, Leibniz integral rule states that if we have an integral whose upper and lower limits are functions of x, suppose the lower limit is u of x and the upper limit is v of x, and here we have a function f of t, and here we have dt. Now, suppose we wish to differentiate this integral with respect to x, then Leibniz rule says that first we'll replace this t by the upper limit, that is v of x. So we have f of v of x, and then we differentiate this function v of x with respect to x, then we have a negative sign, and then we replace this t by a u of x. So we have f of u of x, and then we differentiate u of x with respect to x, right? So when we have a function f which is a function of only t, right? So here we are considering this function f of t only, right? So then this Leibniz integral rule goes like this, right? So here we are given this integral, that is 0 to sine x f of t dt, and here we have square root of 3 over 2 pi x square. So here the lower limit is 0 and the upper limit is sine x. So the upper limit sine x is a function of x. So we'll differentiate both sides of this equation with respect to x. So now differentiating both sides with respect to x, we can write d by dx, and here we have 0 to sine x, and here we have f of t dt, and in the right hand side we have d by dx of square root of 3 over 2 pi and x square, right? So if we compare this integral with this one, then u of x is 0 and v of x is equal to sine x, right? And if we apply this rule, then the left hand side can be written as f of v of x. V of x is sine x, and then we differentiate v of x with respect to x. So we have d by dx of sine x, then we have the negative sign, then we have f of u of x. U of x is 0, and then we differentiate u of x with respect to x. So we have d by dx of 0, and in the right hand side we have square root of 3 over 2 pi, and the derivative of x square with respect to x is 2x. So now simplifying this side, we have the derivative of sine x as cosine x. So we have f of sine x, and here we have cos x, and this term is 0 because here we have 0, and now we can write root 3 over pi, because this 2 and this 2 get cancelled, and here we have x, right? So using the Leibniz integral rule, we have arrived at this equation, right? Now see here, we have to find f of half, right? So here the input is half, and here we have f of sine x, right? So in order to get the value of f of half, let us replace sine x by half, right? So taking sine x is equal to half. This equation is now taking the form f of half, and then we have cosine x, and here we have root 3 over pi, and here we have x, right? So now we need to find out the value of x, and to get the value of x, we'll utilize this relation, that is sine x is equal to half, and this is a trigonometric equation. So sine x is equal to half. It gives us x is equal to pi by 6, because sine of pi by 6 is equal to half, right? And we can see that this x, which is equal to pi by 6, it belongs to this interval, right? So pi by 6 belongs to the interval 0 comma 1, and if we find out the value of pi by 6, then it is approximately equal to 0.523, and 0.523, it belongs to this interval, right? Now see here, sine x is equal to half is a trigonometric equation, and we know that sine x is a periodic function with period t is equal to 2 pi, right? And sine x is equal to half has many solutions, but here x is equal to pi by 6 is the only solution which belongs to this interval or this domain, right? So we have to take only this value of x, that is pi by 6. So now taking x is equal to pi by 6 in this equation, we have f of half, then we have cos of pi by 6, and here we have root 3 over pi, and x is pi over 6. And this pi get cancelled, and we have f of half, and cos pi by 6 is cos 30 degrees, that is equal to root 3 over 2, and here we have simply square root of 3 over 6. So now we can rearrange the terms. So we have f of half is equal to root 3 over 6 multiplied, and here we have 2 over root 3. Now root 3 and root 3 get cancelled. Here we have 2 times 3 is 6, so we are left with 1 over 3. So viewers, the required value of f of half is equal to 1 over 3. So this is how, by making use of the Leibniz integral rule, we can solve these kind of problems comfortably. Hello viewers, in today's session we are going to discuss another important problem from limits of this form, that is 1 raised to infinity, right? So viewers, we have already discussed these type of limits in our earlier videos, and in this video we are going to solve this problem where we have to find out the value of this limit, that is limit x tends to 0, and here we have 5 raised to x plus x square raised to e over x, where e is the famous exponential number. So in this session, we are going to discuss limits of this form, that is 1 raised to infinity. So let us first establish that this given limit is of this form, that is 1 raised to infinity. So for establishing this limit to be of this form, let us assume that the function f1x is equal to 5 raised to x plus x square, and f2x as e over x. So now using this notation f1x and f2x, now this limit takes the form that is limit x tends to 0, and for 5 raised to x plus x square, we can write f1x, and for e over x we can write f2x. So now what we will do, we'll first find the limit L1, that is the limit x tends to 0 f1x. So we are denoting the limit, that is limit x tends to 0 f1x by L1, and L2 by limit x tends to 0, and here we have f2x. So let us first calculate L1. So L1 is a limit x tends to 0, and f1x is 5 raised to x plus x square, right? Now when x tends to 0, then 5 raised to x is simply 5 raised to 0, and for x square, here we have 0 square by simply taking x is equal to 0. So 5 raised to 0 is 1, and here we have 0, so this is equal to 1, right? So L1 is equal to 1, and now L2 is given by limit x tends to 0, and f2x is given by e over x. Now e is a constant, so we can take it outside this limit notation. So we have limit x tends to 0, and here we have 1 over x. Now see, here we have e, and when x tends to 0, 1 over x tends to infinity when limit x tends to 0, right? So this limit tends to infinity. So here we have infinity, and when we multiply infinity with this e, then term this term or this expression also tends to infinity, right? So L2, this limit tends to infinity. So now we see that the value of this limit is now equal to limit x tends to 0 f1x is L1, and limit x tends to 0 f2x is L2, and L1 is equal to 1 because we have just calculated this limit equal to 1, and L2 tends to infinity. So here we have infinity. So this limit is of this form, that is 1 raised to infinity. So here in this session we'll see how we can solve these type of limits which are of this form, right? So here we'll directly make use of an important result which gives us the value of this limit. So now let us consider the case when we have a limit of this form, limit x tends to a f1x raised to f2x, and this limit is of this form, that is 1 raised to infinity. In such type of cases, the direct value of this type of limit can be written as e raised to limit, and here we have x tends to a, and then here we write f2x multiplied with f1x minus 1, right? So the value of this limit is given by this expression, that is e raised to limit x tends to a f2x times f1x minus 1, right? So we'll use this result to get the value of this limit. So now if we compare this limit with this one, then a is equal to 0, because here we have x tends to 0. So the value of a is 0, and f1x is 5 raised to x plus x square, and f2x is e over x, right? So let us call the value of this limit as L. So now L can be given as e raised to limit, and here we have x tends to 0, and f2x is given by e over x, and f1x is 5 raised to x plus x square, and here we have minus 1. So now we can simplify this limit. So we have e raised to, here we can take this e in front of limit notation, and we have limit x tends to 0. And now we can take this x in the denominator of 5 raised to x plus x square minus 1. That is, we can write 5 raised to x minus 1 over x plus x square over x, right? So now we can write e raised to e, and here we have limit x tends to 0, 5 raised to x minus 1 over x, and here x and x get cancelled. So here we have plus limit x tends to 0, and here we have simply x. So what we have done here, we have taken this limit notation to these two terms. So we have limit x tends to 0, 5 raised to x minus 1 over x, plus limit x tends to 0, and here we are left with only 1x. So here we have simply x. Now this limit is equal to 0, because when x tends to 0, then this x also tends to 0. So we have e raised to e, and now this limit is equal to 0, and this limit is simply equal to natural log of 5, because we know that limit x tends to 0, a raised to x minus 1 over x is equal to natural log of a, provided a is greater than 0. So using this standard result from limits, that is limit x tends to 0, a raised to x minus 1 over x is equal to natural log of a when a is greater than 0. Here the value of a is 5, right? And 5 is obviously greater than 0. So the value of this limit is equal to natural log of 5. So now the value of this limit is now equal to e raised to e times natural log of 5, which can be written as e raised to natural log of 5 raised to e. So here we have used the properties of log, that is log m raised to n is equal to n times natural log of m. So now the value of e raised to natural log of 5 raised to e is simply 5 raised to e, because we know that e raised to natural log of say f is equal to f, right? So the value of this limit is equal to 5 raised to e.